Hello guys, myself Assistant Professor Gaurang Prajapati from Mahatma Gandhi Institute of Technical Education and Research Center, Navsari. Today we are going to discuss the topic of plastic design of the subject Design of Steel Structure 8th sem Civil Engineering. Okay, so this is the exam weightage of the chapter, that is this one. So these are the marks of which it has been asked in the previous exams. Okay, so first of all let's start with the theoretical concept, say starting with plastic design concept. So the first one is plastic method introduction. See, the working stress design limits the structural usefulness of the steel up to an allowable stress, or we can say permissible stress, which is well below the elastic limit. For example, yield stress is taken as a design criteria. So, in simple word, what working stress method does, it uses the steel up to the allowable stress only. Over here we can see, okay, which is well below the elastic limit, means the yield stress is taken as a design criteria for the working stress method. Okay, so next point, the working stress method utilizes the strength of steel up to the yield stress, as we discussed in the previous statement, while now in case of the plastic method it utilizes the strength of the steel beyond the yield stress. Okay, for example up to the ultimate load point. So what we saw in case of the working stress method, it uses the steel up to the, we can say, allowable stress, okay, which is well below the elastic limit, while in case of the plastic method it utilizes the strength of the steel beyond the yield stress. Okay, so it uses steel up to the higher category compared to the working stress method. In the plastic method of design, ultimate load is taken as a design criteria. Hence, the structure designing using the working stress method may be heavier than those designed by the plastic method. Obviously, okay. Then the plastic method of the design utilizes the reserved strength of the steel beyond the yield stress, as we discussed in the previous statement, up to the ultimate load point. So the plastic method gives the economical design, and for the plastic design the load factor is taken as 1.7. So this is the introduction of plastic method. Okay, now next point, that is assumptions parameters of the plastic design. See, assumptions made in the plastic design. So first one, the method obeys Hooke's law till the stress reaches Fi, means yield stress. Okay. Next, the yield stress and modulus of elasticity have the same value in the compression and the tension. So yield stress and both modulus of elasticity will have the same value in compression as well as tension. Third point, the material is homogeneous and isotropic both in elastic and plastic sets. So in both the series, say plastic and elastic, the material is homogeneous and isotropic. Fourth, the plane traverse sections remains plane even after the bending and the effect of the shear is neglected. So plane traverse will remain the plane even after the bending, while the effect of shear will be neglected. Then fifth one, the cross section of the beam is symmetrical about an axis through its centroid parallel to the plane of the bending. So cross section will be symmetrical. Okay. Next, the influence of the normal and the shear forces on the plastic moment is not considered. So the influence of the normal and shear force on plastic moment is never considered. Then there is no resultant axial force on the beam. There will be no resultant axial force. Then the material is assumed to be sufficiently ductile to permit the large rotations of the section to take the place. So ultimately materials is assumed to be ductile. So material should be ductile like that. And last one, no instability occurs in any member of the structure up to the collapse. Say up to the collapse, no instability will be occurred. Okay. So these are the assumptions which is made in the plastic design. Then next one, that is plastic bending of the beam. Now, first of all, we can see here, this is the stress strain curve, which as we have already covered in the elementary structural design subject. Okay, there are 4 stages of the any member: so elastic, elastoplastic, plastic, and strain hardening. These are the stages from which the material passes from one stage to another stage. Okay, so now let's discuss about the plastic moment. See, first one, as the moment is increased, the yield stress will appear either in the topmost or bottommost fiber. Say for example, it's some member, say beam. So as whenever the moment will be increased, what will happen? Yield stress will appear either top or in the most bottom fiber. Say this one is the top bottom fiber, this one is the bottommost fiber. Okay. Next, the moment at which the first yield has occurred is called the yield moment. So whenever the first yield will occur, it's called the first, or we can say the yield moment My. Formula will be ZE into Fy, like that. Then with further increase of M, means in moment, the yield will also appear in the bottom fiber and it will spread towards the top. Say for example, let's believe that first of all yield will occur at the top. Okay, now as soon as moment is increased, the yield will start to develop in the bottom fiber also at over here. Okay, then moving forward, with further increase of M, now we are keep improving the moment. It will cause the yield to spread further inwards towards the neutral axis on the top and bottom fiber. So what will happen? So it will keep on increasing towards the neutral axis. Neutral axis is the central axis, we can say. Then a stage will be reached when the yield spreads right up to the neutral axis and the section becomes fully plastic. So ultimate stage will be reached when neutral axis, when both the say top fiber and bottom fiber, the stress from these two fibers will reach the neutral axis at the center. So ultimately at that time the section becomes full plastic. The corresponding bending moment is called the fully plastic moment, MP. The formula for MP will be MP equals to Fy into Zp, where Zp equals to plastic section modulus. Okay. So now let's understand its formula. Fully plastic moment. Say, consider a general cross section of the beam subjected to fully plastic moment. Say for example, it's a section which is subjected to fully plastic moment, say for example MP. Under the action of MP, every fiber of the cross section will be stressed to the yield stress Fy, and the stress distribution will be rectangle as shown in figure. So ultimately under the influence of the MP, means under the action of the moment, every fiber of the cross section will be stressed up to the yield stress, as we already discussed in the starting theoretical portion. Okay, and ultimately stress distribution will be in terms of the rectangle, as we can see in the figure like this. Next, now equating the compressive and tensile stresses, we get Fy into A1 equals to Fy into A2. Say Fy means our yield stress. Sorry. Now say A1 equals to A2, as we can see the upper area is equals to, we can say, bottom area. Okay, so but we can say whole area is equals to the A1 plus A2. So ultimately A1 equals to A2 equals to A by 2, as both areas are the same. Okay, thus the neutral axis divides the section into two equal parts, say passing to the equal stress axis. So plastic moment resistance MP equals to Fy A1 by 1 into Fy A2 by 2. Say take Fy as a common, so we can say A1 and A2 are also same, we can say A by 2. Okay, so that will be A by 2 in the bracket y1 by 2. Y1 and y2 will be the CG of the, we can say, area above and below the neutral axis. So ultimately we will get the formula, just a minute, we will get the formula MP equals to Fy into Zp. Sorry. So MP equals to Fy into Zp, where Zp equals to A by 2 bracket in the bracket y1 plus y2. Okay, so ultimately this will be the criteria of the plastic section modulus. Okay, that stands for Zp, and put down the Zp over here, we will get the MP multiplied with the Fy. Okay, so that is the plastic moment. Now the next point, that is safe factor. Now talking about safe factor equals to plastic moment divided by yield moment. So we can say S equals to MP divided by My, where MP stands for plastic moment and My stands for yield moment. Okay, as we have already seen the formula, MP, that is Fy into Zp, and My, that is Fy into Ze. Okay, so Fy cancel, so ultimately we will get the formula Zp by Ze. So that will be ultimately the formula of safe factor. Okay, safe factor is the property of the cross sectional shape. Say however the shapes of the cross section are it is independent of the material properties. So no matter how the beam or we can say any other material is made of different kind of material. Over here for shape factor is given for the different cross sections. For the rectangle, shape factor is 1.5. For the circular, shape factor is 1.7. For the diamond, shape factor is 2. For the triangle, shape factor is 2.5. And for eye or channel section, shape factor varies from 1.11 to 1.16. Okay. Now, advantages of plastic design. So first one, saving of the material over the elastic method resulting in the lighter structure. So ultimately using the plastic method we can save the material, so ultimately it will be economical as well as it will be light in the weight. Then realization of the uniform and realistic factor of safety for all the parts of the structure. So it's provide the factor of safety for all the parts of the structure. In case of the elastic method, factor of safety varies, while in this one factor of safety will always remain uniform. Then design moment can be calculated rapidly. Design moment can be easily calculated within the shorter time. Then fourth one, it gives an idea about the type of collapse and the strength of the structure. So it will gives idea about the two things, the strength of the structure and the we can say idea about the types of collapse. Then in plastic design, the balance section is obtained in a single attempt, while in the working stress method design process is repeated several times to obtain optimum solution. So in the plastic, so in simple words, in the plastic design balance sections can be very easily achieved, while in case of the other method we can say working stress method, we have to sorry, we have to try several times to get the optimum solutions. Then sixth one, no effect due to the change in temperature, settlement of support and imperfection. So because of this criteria, say change in the temperature or we can say settlement of support or we can say imperfection, there will be no effect on or we can say change in the design. The last one, design is very popular for the design of beams and portal frame. So it is useful or we can say popular for the design of beam and portal frame. Okay, so these were the advantages of the plastic design. Well, there are some disadvantages are also there. First one, there is a little saving in the column design. Say in case of column design, it will be saving will be less. Second one, it is difficult to design for the fatigue. So it's very difficult for design of fatigue. Then if structure is complicated, it is difficult to obtain the collapse load. When structure is easy, collapse load can be easily achieved, while in case of the difficult design or we can say complicated design, collapse load is hard to obtain. And fourth one, lateral bracing system requirements are more strict than the elastic design. So compared to the elastic design, lateral bracing designs are more stringent. Okay. Okay. Next one, that is plastic hinge. So let's first resolve the theory, then I will explain the concept of it. See, plastic hinge is a zone of yielding due to flexure in a structural member. So first of all, plastic hinge is what we can say zone of yielding due to the flexure in the structural member. So plastic hinge in simple words, it is also known as zone of yielding. Then second, consider a simply supported beam loaded by gradually increasing concentrated load W at the midspan. Okay. Then the increase of the load causes the increase of the load causes proportionate increase in the maximum bending moment at the midspan. Since the rotation is proportional to the maximum strain, the moment of the resistance proportional to the maximum stress. See, in simple word, say let's take a simply supported beam, put the gradually increasing load or at the midspan we can say W. So what it will do, it will create a deflection over here like this. Okay. So whenever we are increasing this load, ultimately it will also increase the moment because moment is directly proportional to the weight. Okay. So ultimately stress will also be produced in this one. So stress will also be higher as the load is increased. Next, the moment rotation relationship is shown in figure. Okay. Then with the increase in the moment, a stage is reached where the maximum stress in the outermost fiber reaches the yield stress Fy and the corresponding moment My. So whenever you are keep on increasing the moment, it will reach at a stage when moment will be maximum or stress will be the maximum stress, we can say yield stress. Then just a minute. With increase in moment, say m equals to m greater than my, but less than mp, say it is greater than the yield strength but the less than, we can say, plastic moment. Okay, part of the outer section becomes full section, full plastic, while the inner portion near the neutral axis still remains the elastic. So what will happen, the part of the outermost fiber, for example this one is the beam, so outermost fiber, it will becomes the plastic, while the inner one will still remain the elastic. Okay, therefore the section is called elastoplastic condition, as it is, as we have already seen the 4 different stages of the section. Okay, elastoplastic is one of them. Then as the load increasing, a stage is reached when the entire section becomes the full plastic and the section is no more in a position to offer any additional moment of resistance, and the section simply rotates under the constant moment. Okay, at the center of the area there will be fully plasticity over the full depth of the section, and the section will behave like a hinge. This is called the plastic hinge. Okay, at the section of the plastic hinge, the restraining moment is equal to mp. So let's understand this theory in a simple manner. Say let's take a simply supported beam over here like this and apply the central load over here. The cross section of the beam will be like this. So this one is our neutral axis. Now whenever I am keep on increasing this load, okay, so what it will create, it will create a moment, as moment is directly proportional to the strain, and at the same time stress will also be produced because stress is directly proportional to the force. Okay, so it will it will create a stress. So whenever we are keep on increasing our load, so ultimately it will also keep on increasing moment as well as it will keep on increasing its stress. So ultimately a stage will be reached when the stress becomes the fully plastic, not fully plastic, say first of all it will achieve the yield stress. Okay, and the moment will be applicable, that is greater than, we can say, the yield moment, and but it will be less than a plastic moment. So what will happen, it will create fully plasticity at the outermost surface of the beam like this over here, this one and this one, while the inner one will still remain the elastic. Say this is called elastoplastic material. But if we keep on increasing the load as well as moment, and we can say alternatively stress, so ultimately the whole section will become completely plastic and it will keep on rotating on just one point. Okay, that one point is called, we can say, hinge, and that is known as plastic hinge. So this is the basic concept of the plastic hinge. Okay, or we can say simple word, talking about the SA1 deflection manner. See, this one is a simply supported beam. Now we all know that maximum bending moment occur over here at the center, as well as maximum deflection will also occur over here at the top, at the center. So if we are keep on increasing our load, at one time it will be behave like a completely plastic material. It will keep on rotating this point. Okay, then this point is known as plastic hinge. So this is the concept of the plastic hinge. Now the plastic hinge occur at, see, plastic hinges occurs at number 1, plastic, just a minute, let me zoom the figure. See, plastic hinge from in a member at the maximum bending moment location. So first plastic hinge will occur at the maximum bending moment. Then however, at the intersection of the two members where the bending moment is same and a hinge is formed in the weaker member. Okay, so whenever the, say, at the intersection of the point means, say for example a frame is there, so this one is the intersection point, so at intersection point also the plastic hinges will occur. Then generally hinges are located at the restraint and intersection of the member and at the point load. For example, this one is my support, so over here, and the location of the point load means it will create over here also. Then at the connection involving the changing in the geometry, for example, say a beam is there whose geometry is different like this, so it will create over here also as geometry is changing at this point. Okay, so plastic hinge will produce over here also, and at the point of the zero shear force in the span loaded by the UDL. Okay, so these are the criteria where plastic hinges are formed. Then let's talk about the some other definitions also. Say load factor Q, say Q equals to WC by W or WL by W or WU by W. Okay, where Q is stands for load factor, WC, WL, WU, these are the collapse load or we can say limit load, and capital W, this is known as working load. Next one, that is collapse load. We have seen over here collapse load. So what do you mean by collapse load? So let's say the definition. The load at which the sufficient numbers of the plastic hinges are formed in a structure such that a collapse mechanism is created is known as the collapse load. Okay, so at that load where plastic hinges are formed and those plastic hinges will create a mechanism, okay, collapse mechanism. So that particular load is known as collapse load. Say Q equals to S cross F. So ultimately collapse load formula will be W multiplied by F, where W equals to working load and F stands for factor of safety. Okay, so this is the theoretical criteria. Now let's see some of the examples regarding the safe factor. We have already seen the formula of the safe factor. Just a minute, over here. Zp by Ze, plastic section modulus divided by elastic section modulus. So first of all, rectangle section. Just a minute. See, determine the safe factor for a rectangular beam of the width b and depth small d. Okay, now as we can see, just a minute. See, a rectangle section is there, that is this one. Okay, of the width b and depth, that is small d. Now talking about CG, we know that the CG will occur always at the center, say d by 2 and d by 2, like this one is my CG, or we can say y bar, like that. Okay, but we need, okay, that we will discuss later on in the example. Okay, now over here already we have seen in the formula, say for the same area above and below the neutral axis, so ultimately stress distribution in case of the, it will occur in the rectangle shape in the equal proportion. Top portion is compression while bottom portion is in tension. So we need to calculate the safe factor of it. Now the formula for the safe factor is Zp by Ze. Now Zp stands for plastic section modulus, Ze stands for elastic section modulus. Okay, so first of all, we know that if we want to calculate safe factor, first of all we need to calculate Zp as well as Ze. Now talking about Zp, we have seen the formula in the theory. Zp equals to a by 2 in the bracket y1 plus y2, while Ze, the formula for Ze equals to I divided by y max, means moment of inertia divided by center of gravity. So for that we need 4 unknowns, y1, y2, this one, area, and we can say moment of inertia and CG. So ultimately 4 unknowns will be required. Okay, so whenever we are solving any kind of safe factor sum, so first of all we need to solve these 4 unknown parameters, then put down it in the Zp and Ze, so we can easily get the safe factor. So let's solve first of all. So talking about first unknown, that is area. Now we know that rectangle section is there, width is b, depth is d. So ultimately area will be, we can say, b cross d. That's the basic equation of the area. Now talking about y1 and y2, so let me zoom the figure first of all. Okay, talking about y1 and y2, so we have studied in the MOS. Okay, say y1 is the, we can say, CG of the area above and below the neutral axis. So for example, we are considering the portion above the neutral axis. Okay, so ultimately this depth is d1. Okay, talking about its y1, so y1 will be the CG of this one with respect to neutral axis. So this will be my y1. Now we know that this one is d of the rectangle section, so ultimately y1 will be equals to its center, we can say d by 2, that is the above portion of neutral axis. Now let's do the same thing with the below portion. Say this one is our neutral axis, now this one is our portion. Okay, now talking about CG will be over here, so this will be my y2. Say same parameters, whole dimension is, we can say, d by 2, so the half dimension will be, we can say, d by 4. So we got two things, say y1 and y2 both equals to, we can say, d by 4, this one. Okay, so so y1 y2 that is equals to d by 4, area that is b cross d. Now y, rectangle sections moment of inertia formula, that is obviously bd by 12, and talking about CG of the rectangle section, that is always at the center, d by 2. So we got all the 4 unknowns parameters. So first let's calculate Zp. The formula of the Zp stands for a by 2 in the bracket y1 plus y2. Say talking about putting down about the value. So first of all area, that is b cross d. So let's put down the area, that is bd divide by 2 in the bracket y1 and y2 both are equals to d by 4. So d by 4 plus d by 4. So let's solve this one. BD by 2, and in the bracket we can say d by 4 plus d by 4, so ultimately it will be d by 2. So ultimately let's solve this one. So ultimately we will get BD square by 4. So this is the value of the ZP. Now talking about ZE, that is this one. Formula stands for I by Y max, Mi upon Cg. Talking about Mi, BD cube by 12. Talking about Cg, d by 2. So simplifying this one, we will get the BD square by 6. So once we got the value of Zp and Ze, so I can easily calculate the value of safe factor. Safe factor stands for Zp by Ze. Zp, that is, just a minute, Zp BD square by 4, and Ze, that is BD square by 6. So BD square will be cancelled, so ultimately it will be 6 by 4, that is 1.5. okay. I have already given this safe factor over here. You can see for the different, all the different sections, you can see for the rectangle safe factor is 1.5. okay. So this is the derivation of this safe factor. Let's take another cross section, say circular section. Now determine the safe factor for a beam of the circular section of the radius r. okay. Now so first of all, let's draw a circle of the radius, we can say r. So we need to calculate safe factor. Once again, the same parameters we need to for safe factor we need to calculate the value of Zp and Ze. Zp, this formula same, a by 2 in the bracket y1 y2 means y1 plus y2, and Ze, that is I by Y max. So once again we need 4 unknown parameters: area, Cg, y1 y2 and Mi. So let's start with first unknown. First unknown means area. Now we know that for the circular section of the radius r, area will be, we can say obviously pi r square, or in case of the diameter we can say pi by 4 d square. Now talking about Mi, so talking about Mi, so for that one we know that for the circular section the Mi's formula is pi by 64 d raised to 4. okay. And talking about Cg, Cg is always at the center, so we can say it is either, we can say d by 2, or we can say radius r. That will be the criteria of this one. And talking about y1 y2, then talking about y1 and y2, so we all know that we can say, for example, just a minute, let me take, say talking about y1 y2, we all need, for example, for we are taking half circles, and those Cg with this one, that will be, we can say 4r by 3 pi. So same criteria will be over here, say above the neutral axis, and below the neutral axis obviously it will be again the same criteria, that is 4r by 3 pi. This one is our y1, while this one will be our y2. So we got all 4 unknowns: area pi r square, y1 and y2 both 4r by 3 pi, I pi by 64 d raised to 4, and y max, that is, we can say radius, or we can say d by 2. So now let's put the value of this one in the first of all Zp. Formula stands for a by 2 in the bracket y1 plus y2. Now talking about area, that is pi r square, so pi r square by 2 in the bracket y1 y2, both values are the same, 4r by 3 pi, 4r by 3 pi. So ultimately solving it, we will get 8r by 3 pi whole multiplied by pi r square by 2. So simplifying this one, we will get the value 4 by 3 into r raised to 3, or we can say r cube. Now the next unknown parameters, that is elastic section modulus, Ze. Formula stands for I by Y max, Mi upon Cg. Mi pi by 64 d raised to 4, while Cg, that is, we can say d by 2. So simplifying this term, we will get pi by 32 d cube, but we have got the value of the Zp in terms of the radius. So let's convert it this one also into radius. So put down d equals to twice r, so pi by 32 into 2r cube. So ultimately we will get pi by 4 into r cube. So ultimately we got the value of Zp, okay, and Ze, this one. So now let's find the safe factor, that is Zp upon Ze. Zp 4 by 3 pi r cube, and Ze pi by 4 r cube. R cube will be cancelled. Ultimately it will be 16 by 3 into pi. So simplifying this one, we will get the value 1.698. So ultimately the final safe factor will be 1.7. okay. So this is one, this one is a safe factor of the circular section, as I have given already earlier. This one for the circular section, s equals to 1.7. Similarly, we can obtain the safe factor value for diamond, triangle, and I, or we can say channel section. okay. So these were the typical cross section. Now let's solve some of the sums of the GTU Now just a minute. Example number 3. Determine the shape factor for an I section consists of 8 mm thick web and 12 mm thick flange. The depth of the web excluding flange is 300 mm. The width of the flange is 120 mm. Okay, so first of all let's draw the figure. Now I section is there, so let's draw the I section first of all. Okay, now talking about dimensions. 8 mm thick web, so thickness of web is 8 mm. 12 mm thick flange, thickness of flange is 12 mm. The depth of the web excluding flange is 300 mm. This one is the depth of flange, this dimension. Okay, and width of the flange is 120, and that is we can say over here. Okay, so first of all we need to do this figure. Now let's understand the basic criteria. See, say CG will be obviously at the center as symmetrical I section is there. See, at the top and bottom both flanges are same, so I section is of the symmetrical section, so CG will be at the center. Say depth of web is 300, so this will be at the center, that is 150. Okay, whole CG of the I section, that will be we can say overall depth, that is 324, so 324 by 2, so ultimately it will be 162. Okay, how we get 324? So summation of all these three dimensions, 12 plus 300 plus 12, so ultimately it will give us 324, and CG it will be center of this one, so 324 by 2, so we will get CG 162. We will use this data in the calculation then. Okay, so we need to calculate shape factor, that is ZP by ZE. So first of all let's solve first of all ZP. Now for symmetrical section, the formula of the ZP will be we can say 2 times A1 by 1 plus 2 times A2 by 2. Means what we need to do, say we will solve the area above the neutral axis, we will calculate ZP this one, and we will multiply it with 2 to get the value of below portion. As it is a symmetrical section, so above and below neutral axis the area and cross section is same. Okay, so first of all ZP formula stands for A1 by 1. Just a minute. See, formula stands for A1 by 1 and A2 by 2. Just a minute, let me zoom in. Okay, so there are two sections above the neutral axis. See, first of all this one is our flange. Okay, and second that's our web. So we need to calculate area and its CG means y1 with respect to neutral axis. So first of all let's talk about first section, that is flange. Its area, say 120 multiply by 12, say 120 multiply by 12, and talking about its CG with respect to neutral axis. Okay, so its CG will be at the center, we can say this dimension. So center of the flange 12, so 12 by 2 plus this dimension is 150. Okay, plus we can say 150. So ultimately it will be 120 multiplied by 12 into, simplifying this one, I will get 156. So it will be A1 by 1 of the top flange portion. We can see over here 120 multiplied by 12 multiplied by 150 plus 6. Okay, now talking about second portion, that is this flange with respect to neutral axis. First of all talking about its area will be we can say thickness is 8 mm, so 8 multiplied by 150, 8 into 150, and talking about its CG, say its CG will be we can say at the center with respect to neutral axis, so overall left is 150, so CG will be 150 by 2. Okay, so see we can see over here 150 into 8 into 150 by 2. So what we have done, we have calculated A1 and Y1 of the both the section. First of all this flange, and second this web, both with respect to neutral axis. Okay, so simplifying this one, we will get the value of ZP, that is 629.28 into 10 raised to 3 mm raised to cube. So Z-split problem has been solved. Now talking about ZE, we know that Z equals to I by Y max. So we need CG as well as MI. First of all talking about CG, so CG is always at the center. Say with respect to bottom it is always at the center. Say D by 2. So D, that is 12 plus 300 plus 12. So overall depth is, we can say, 324. Say 324 by 2. So ultimately we will get, that is 162. This one. So we got the y max also. And talking about mi. So as this is a symmetrical section, we can use the box method to get the moment of inertia directly. So what we need to do, first of all, we need to consider it as a box. So first of all, mi of the whole box section, that is 120 into 324 cube by 12. Okay, now from this one deduct this portion, this one as well as this one. Okay, so remaining one, so this we need to deduct these two area from that one. So out of 120, this thickness of wave will be deducted. So 120 minus thickness of wave, that is 8, whole multiply by this dimension, this depth of wave, that is 300. So into 300 cube by 12. So doing this one, we will get the mi of the symmetrical eye section directly. See, I am highlighting the eye sections area, this one. So we will get this mi of the symmetrical eye section. This is called the box method. Okay, you can see over here, I see 120 into 324 cube by 12 minus 120 minus 8, that is thickness of wave, into 300 cube by 12. Okay, you can apply this one only in case of the symmetrical eye section. So we'll get the mi, that is 88122.24 into 10 raised to 3 mm raised to 4. Okay, so once we get mi and cg, we'll get ze. Z equals to I by y max. I, that is this one, put down over here, and y max, that is 162, put down over here. So ultimately we will get our answer of Z 543.96 into 10 raised to 3 mm cube. Finally, safe factor equals to Zp by Zd. Zp, that is 629.28 into 10 raised to 3, while Zd 543.96 into 10 raised to 3. So ultimately we will get the safe factor, that is 1.16. Clear? So this is the safe factor of, we can say, any built up section. Okay, now next sum. Now let's take any roll section and find safe factor of this one. See, roll section is such kind of section which is directly available in the market, while built up section is such kind of section in which we make, or we can say we connect flange and wave to connect it, to make it as a I section. Okay, so this one is known as built up section, while our different sections, say for example ISMB 600, ISMB 300, these all are our roll sections. So let's solve the sum. Example number 4. An ISLB 300 section is used as a simply supported beam of the span 5 meter. Okay, ISLB 300 section is given, that is roll section, and its length is given as, so we can say 5 meter, simply supported beam. Find the safe factor for the beam section. Okay, if the beam carries a point load 80 kilonewton at the midspan, again this one was our beam, L was 5 meter. So it is simply supported and 80 kilonewton load is acting at the center. So it will be 2.5, 2.5. Okay. Find the collapse load and the load factor also. Take Fy equals to 250 Newton per mm square. So first of all, for ISLB 300 section is given. In the previous video lecture also, I have taught you how to take these properties from the steel table, or we can say from IS 800. These values can be derived, or we can say this is the property of ISLB 300. Okay, this is the property of ISLB 300, which we can easily get from IS 800, page number 128 and 38, I think. Okay, so from that one we can easily derive this value. Okay, let me show you, just a minute. We are going to the IS 800, page number 138. See, Over here different role sections are given. Our property, we need to find the property of ISLB 300. ISLB 300 is, just a minute, let me search it first of all. Okay, ISLB 300 is over here, just a minute. ISLB just 300. Okay, as you can see, we need to take its area, we can take its depth, width of flange, width of web, thickness of web, radius of gyration, section modulus or plastic section. We can get its all the values. Okay, so we have got all this property from over here. Okay, let's get back to the sum. So we have got moment of inertia, I Z Z, ZE, elastic section modulus, thickness of flange, thickness of web, width of flange, and height, that is 300 mm, or we can say depth. Okay, so similarly as we have done in the previously, ZP, that is 2 times A1Y1 plus A2Y2. Okay, talking about A1Y1, say we need to calculate this one with respect to neutral axis. Say its area and its CG with respect to neutral axis. Area 150 into 9.4, that is flange dimension, with respect to CG. Its CG will be at the center, say 9.4 by 2, and this one will be the overall depth. Say this 140.6 has been derived from, let me show you, the overall depth of the section is 300 mm. Now thickness of flange is 9.4 at top and bottom, so the remaining one will be this one. Say out of 300, we can say we have to deduct 9.4 plus 9.4, so total 18.8. so ultimately it will be 281.2. this depth of the, we can say, wave, and dividing it by 2 times we will get this value, 140.6, 140.6. Okay, so hope so you have got the concept. Okay, so what we are doing over here, say this one is our flange, we need to calculate its area and CG with respect to neutral axis. Its area, say 150 multiplied by 9.4, just a minute, let me show you on this side, 9.4. and talking about its CG will be always at the center, so from center the dimension of neutral axis, this one will be 9.4 by 2 and this will be 146. Say so its area will be this one, 150 into 9.4 A1, and its CG 140.6 into 9.4 by 6. Okay, and similarly this wave's area and CG with respect to neutral axis, its thickness of wave, that is 6.7, just a minute, 6.7, and this depth is 140.6. okay, so its area 140.6 into 6.7, and talking about its CG will be always at the center, so 140.6 divided by 2. so ultimately we will get it multiply with 2 times because the same area is there. Okay, like that, so we will get ZP 542.19 into 10 raised to 3. While talking about ZE, say elastic section modulus, so until now what we were doing it, or we can say we were calculating it by doing the ratio of MI with respect to CG, but as it is a roll section we can directly take its ZE from the property. So we have, from the property we have already got the value of ZP. So now for safe factor equals to ZP by ZE. ZP is this one, 542.19 into 10 raised to 3, while ZE 488.9 into 10 raised to 3. So ultimately safe factor will be 1.109. Okay, so guys, these were some of the examples of the safe factor. Hope so you have got the concept of the safe factor. Okay, thank you.